A very good afternoon to the course participants of this 13th EduSet program on remote sensing GIS and GPS. I am Vandita Srivastav. This is module 3 on GIS, and today we will discuss some things on spatial data analysis. This topic has already been covered or introduced to you by GPL and Raju, sir. I would be discussing with you on functionalities and tools in detail. So let us have a look at the agenda for today. This is the total agenda for spatial data analysis, out of which some has already been covered, and I would be covering the rest. The green color here shows the ones that are covered by Raju sir. So why spatial analysis? And what is spatial? I will also talk a little about this, what is spatial in spatial analysis, and spatial queries and non-spatial queries were also discussed by Raju sir, but then I would discuss more on that, and what are various types of analysis we will discuss at the end. These things we will discuss at the end, and we would then start with the retrieval and selection operations, measurement and reclassification operations, overlay operations, which includes the common functions as well as the vector and raster based overlay analysis, and network neighborhood and connectivity operations, which includes network analysis. But since network analysis would be discussed in detail by my colleague in later sessions, so I would discuss about network analysis in short. And then at the end we would discuss about various types of spatial analysis that are possible in GIS. So let's begin with the introductory quick overview of the GIS spatial analysis. Now, what is special about spatial analysis in GIS domain? You know that there are existing CAD packages which deal with the spatial information. Similarly, you have the database management packages which deal with the attribute information. So what is that which makes a GIS spatial? And it is the linking between these two type of data, that is the attribute data and the spatial data, which opens up enormous opportunities for us to analyze these data together. And that is one thing. The other thing is that since we are talking about geographic information, we can answer all the questions that are of type geographic or which are of spatial relevance in other terms. So here are the 5 questions, popular questions, which you would already be knowing, 4 W's and 1 H, what, when, where, why, and how. And these are all the questions of geographics and geographic nature. That is, in the question itself, they have the geographic component. And we can answer these questions with the help of GIS, with the help of spatial analysis tools. An example of such a function is, what are most suitable locations of a dam? If I am going to construct a dam using remote sensing and GIS technology, what would be the most suitable locations? So what basically I am trying to do here, I am trying to achieve or prescribe a model for some sites which are most suitable locations for construction of a dam. I would be considering all the respective criteria relevant for this study, and I would come up with a prescriptive model. How exactly this will happen? For that you would need a lot of tools that we'll discuss in this lecture. We'll discuss about a lot of tools which could be helpful for answering such type of questions. But then whenever I am trying to prescribe, it is called as prescriptive modeling. Another type of questions could be how fire will progress or spread in next 2 days. Suppose fire has ignited at one point. Now how it is going to spread in time and how it is going to spread in a space, let's say in next 2 days. So I have some information, but I am trying to predict for the future. So this is kind of a predictive modeling, and both of them, these questions here involve geographic information, so they can be answered with GIS. Please note here that anything which does not have a spatial reference or spatial relevance, for example, books in a library, they have their own independent library information system, but since the geographic relevance is not there, so we would not like to study such type of phenomena or such type of systems with GIS. So spatial relevance is very important, and the other important thing is the linking between the spatial and the non-spatial information, which makes GIS spatial for spatial analysis, and it actually doubles the capabilities of spatial analysis in GIS domain. So we have already seen the querying. Raju sir has already shown you the attribute and the spatial query. These are the most simple and basic steps in any spatial analysis project. But the scope does not end here. It is rather the starting point. That is that we start with attribute and spatial queries, but then we go on to generating new data sets from original database by applying a lot of tools. So there are a lot of tools available in GIS, any GIS software, which would enable us to do spatial analysis. And the queries in the real world would not be simply an attribute query or simply a spatial query. It will be rather a very complex combination of these queries and some more tools, which would enable us answering the questions that I just showed you. So querying and there are a lot of other tools which can help us query our database as well as perform various types of analysis. And these functions are classified into following categories: retrieval and selection operations, measurement and reclassification operations, overlay operations, which include raster and vector based overlay operations, and neighborhood and connectivity operations. If you carefully look at the classification of the functions itself, the retrieval and selection functions are the most simple and most basic operations that could be performed on GIS layers. Retrieval and selection operations do not involve any kind of editing of geographic location or any kind of manipulation of data set. Measurement and reclassification operations mean producing some new information. While the previous two did not produce any new information, they rather retrieved the information that was already existing in the database. Measurement and classification operations would produce some new information, but again they would not, so they are doing some kind of manipulation, but they are still not editing the geographic location, they are not cutting the features, new topologies are not built. So measurement and reclassification is the second category. And third category is the overlay operations, which involve cuttings, intersections, definition of the geographic location of features also changes. So all such things are involved in overlay operations because intersections take place, so new topologies are built, new features are created. We would see this in detail in the later slides. And then finally, neighborhood and connectivity operations. Previous three operations, they do not specifically talk about what is around us. Neighborhood and connectivity operations are such operations which are considered not just the cell at hand or the location at hand, but also its surroundings. So we'll discuss about all these operations in detail. Let us start with the very basic operations which are required not only for retrieval, they are required for retrieval, selection, overlay operations, and these are all very basic operations. They have also been touched upon by Shri Raju sir. You know them all, they are all very simple operations. I need not tell you what exactly they are, but what I am going to focus is how they can be used in GIS. For example, you can have all kinds of arithmetic and other operations, trigonometric operations, division, multiplication, and all such operations. Here is an example. Raster 2 is equal to raster 1 multiplied by 5. Now, it is simple operation, multiplication of a grid by a number 5. But how do you visualize it? How do you use it is what that makes it different. So if you, for example, imagine raster 1 to be a digital elevation model, a grid which represents the elevation values. Now, if you multiply that by a number 5, what exactly will happen? What will be the effect of it? It will be an exaggeration, right? Because we are multiplying the values by a number 5, it will be exaggerated. Now, once the values are exaggerated, the differences which were very minor will also be exaggerated. So we would be able to see them, we would be able to visualize them, we would be able to perceive them. So that is what we can use a multiplication for in this example. So similarly, there are other possibilities. How we use these operations is what is that makes the use of these operations unique. And that is what is left on our innovation. Another example is of relational and comparison operations, which are again, they are all available on your keyboard. Now, how I read the relational statement, we say like this: C is assigned as A not equal to B. This symbol less than, equal to, and greater than, less than and greater than makes it not equal to. So some software would represent it as an E, others would represent it as with a hash sign, while some other software would represent them as less than and greater than. So C is assigned as A not equal to B means C will be true when A is different from B, right? So if A and B both are same, then C will result into a 0. So this is a Boolean statement actually. Now what exactly this means and what can it give us? If you think A and B as maps of the same area, for example, you could think of let us say maybe a land use map for Dehradun in the year 2010 and 2000. Now when I perform this operation C as assigned as A not equal to B, the C will have value 1 wherever the land use of Dehradun changed from 2010 to 2014. Wherever it did not change, that is wherever A and B were same, it will result in a 0. So finally, C is nothing but a change detection map, which has detected all the changes in the land use of Dehradun from year 2010 to 2014. So again, this is our imagination how we can use this simple relational operation for our benefit. Another example, a very simple example is area, or the syntax is like this: field less than, field relational operation and then value. So field could be area, relational operation could be less than or greater than or whatever of this list, and value could be again based upon what is available in the data set. So when I perform this query, area less than 400,000, I should get all the polygons. Let us say I'm talking about the land use map. So area in a land use map, all the smaller polygons which are having area less than 400,000 should result. Now let us see how it looks like. The result is like this. This is a land use map, and you would notice that anything which is less than 400,000 has resulted. Now you can see that they are smaller polygons. The bigger polygons are not resulting. I could not show you the whole table, but you would see that anything which is more will not be shown here. Then we can also use the third category of operations, that is logical operations. Again, they have been talked about by Raju sir, so I would not deal with more on that, but I would show you some example. So AND, OR, NOT and XOR, and I guess he has shown you examples on raster analysis, the use of logical operations and rasters, so I would show some example on vector. Now out of these 4 operations, AND, OR, NOT and XOR, the first 3 operations are the basic operations, and this one is a derivative. That is, you can derive it from AND, OR and NOT. Now this is a thought for you. I am posing a question to you basically, how we can derive XOR from these operations. There are some more than one possibilities, so I would like to hear from you after the break your answer, how we can derive XOR from these 3 operators. Okay, I hope you have all noted it down. Now we work with operations, these AND, OR, NOT and XOR. There are 2 things in any logical operation: the operands and the operator. So operands are nothing but the data elements A and B. So when I say A and B are the data elements and AND is the operator. So operator establishes a relationship among the data elements. Now what this A and B mean, that you already know as such, but I'll just give you a quick example. And finally, the cell value of the output raster is either true or false. Please notice here that this need not be raster. It could be raster or vector. So AND can be performed on both raster and vector data set. This slide was covered by Raju sir, so I would not highlight more on this. Only that you have to tell me how XOR can be derived from AND and OR and NOT. Now, this is an example performed on the vector layers. Land use is forest, slope is steep. These are two conditions, A and B. Now, when I combine this and this using AND operation, only those places which satisfy both the condition of land use as forest and the condition of slope as steep will be resulted here. Okay, if this was OR, then either OR condition would have applied. That is, either it can be a forest or it could be a steep slope. But here, since the operation is AND, we get lesser area. If we performed an OR operation here, we would get more area than what we see as a green color. Right, so you can use logical operations and relational operations and conditional operations for performing simple retrieval and selection queries as well as some operations. They could be part of some complex analysis steps. Now, what are retrieval and selection operations? We would discuss. So we can have, we can use pixel information window, then there are, this is for retrieval. For selection, we can have interactive selection, that is very simple, and selection by attributes, selection by spatial relationships. So this is something that would be new for you. I will discuss with you spatial relationships, and then I would also give you some small assignments for finding out areas with using spatial relationships. So retrieval, you all understand, data retrieval involves selective search, manipulation and output of data without requirement to modify, as I told you, without requirement to modify the geographic location of the features involved. So linked spatial and attribute data are retrieved, but no changes are made to the location of spatial elements. And no new spatial elements are created. Only from the existing data set, some of the features are selected and retrieved. Right? Then when we use retrieval, whenever we have to find out what exists at a particular location, what is at this particular location, such queries we would use retrieval operations. Retrieval of a spatial data such as all these features, points, lines and polygons, or the raster pixels, which are an answer to question where is forest or where is a steep slope, for example, is again a type of retrieval question. Retrieval of information using logical and arithmetic operations is also possible. So this is retrieval using pixel information, and this is an example from Ilvis software, wherein what we do, there is an open this pixel information window which is opened here, and we have dragged the three maps, soil, rock and slope, to the map window. Right now, by moving our cursor in this map window, all the information that is pertaining to these three layers will also keep moving, keep changing here. So for example, for this particular pixel which is shown here in the slide, you will see the row and column, because this is a raster, you get the row and column, and also its XY, and whatever is information is stored in these three maps will also be shown. For example, the soil type is 2 here, the soil is silt, the thickness is 5. Similarly, in the rock layer, the type of rock is 3, it is granite, and the strength is high. And in the slope map, you find that the slope is gentle. Just by moving a cursor here, just because we have digitized all these layers and stored them as database, we can retrieve, just sitting on our computer, we can retrieve so much of information just by this simple tool called pixel information window. This is an example where we have dragged all the information to the map window. Similarly, We can also drag all the information to the pixel information window instead of dragging the information to the map window. That is, you notice here that only one map is displayed. Other maps are not displayed here because it may make the look or the view very messy. So to avoid that, instead of dragging the information here, we drag the information here. So you can see that geology, then lithology, use, DEM, rainfall, all the information is to this pixel information window. Now if I move my cursor here in this map window, again I will see a change in these values. So this is a quick retrieval of information. Before I can start my spatial analysis, I should always do this kind of retrieval so that I know what is where and how do I design my queries and various spatial analysis steps. So this is a quick initial step to any spatial analysis project. Also retrieve using map calculator. For example, if I want to see only the grass out of all land use, I want to see only grass. I know that grass is stored as land in the attribute table. So I can simply launch this query on the command prompt. I say grass is equal to land use is equal to grassland. That would give me a 1 wherever I have grass, otherwise it will give me a 0. So the outcome of all these statements would be, of this statement would be a Boolean outcome, that is 0 and 1. 1 wherever I have grass and 0 where there is no grass. Similarly, we can use if statement, and here I will not get a Boolean output, rather I will get a string, the class domain, that is water and land. If land use is lake or land use is river bed, then give me water, else give me land. So a land use map which may be having some 12, 13, 14 categories is now categorized or classified as only 2 categories, water and land. All other which are belonging to the land class have gone to land, and the ones that are belonging to water features are categorized as water. So this is again a quick step to see where exists water and where exists in the land use map that I have. Then another example is that you could say fault is equal to fault and length is, so here you are combining 2 maps. So in fact 2 informations, fault wherever I have fault and the length is more than 5,000. So I can also, these are examples which combine 1 or 2 maps. I can combine even more number of maps to execute such statements. So I can have a quick retrieval of information in this manner using map calculator. Then we come to the spatial selection queries. As I told you, we can have interactive selection. We can use attribute conditions using the relational, logical, and combining various types of attribute conditions. And most importantly, we can use spatial topological relationships in order to perform the selection queries. I would, in a minute or so, I will show you these topological relationships. An example of such relationship is that selecting features that are inside objects or selecting features that intersect, that are adjacent to, that are at a distance from. So these are all the types of spatial relationships. Now this is the simplest form of selection, interactive selection. You open a table, click on a record here, select a record, and corresponding polygon would be selected. Other way around, you can also do, you drag your selection window into, let us say, a window or circle, and whatever area that is connected to it will be highlighted and it is selected. And when you open the attribute table, corresponding records are also selected. So this is simple interactive selection. We have not applied any query or any other tool. We have just used the simple selection, the arrow tool to get the selection. There are other possibilities using the SQL queries, display the results both on the map and in the attribute table. That will be always the case whenever we make selection. The selection will be both in the spatial map as well as the corresponding attribute table. And we can answer questions of type, what are the features, where are the features with so and so conditions or so and so criteria. So these kind of questions can be answered with the spatial selection queries. And an example is again here using the logical operators and the relational operators. These are simple examples which you have already seen in the raster domain, and also I just showed you for the end of land use is forest and slope is steep. So this is again another example of area less than 400,000 and land use is equal to 80. Now you see in the previous selection where we had launched this query, area less than 400,000, we saw many more polygons. But since we have put an additional condition of land use is equal to 80, this whole statement is satisfied only when both the conditions are met, because the operator here is AND. So only few records are selected and the area is again very small. The bigger polygons are not selected. You see that the land use more than, even the area is less than 400,000, but because this is not land use 80, so these are not selected here. Right? So can do that. Now spatial relationships are as follows. I'm sorry that animations cannot be run because of the restriction on animations. I could not show you this, otherwise in the classroom we show it in an animated manner. But anyway, only equal to would be little difficult to, I'll explain it to you. The disjoint means, let us say we have two features A and B, right? Now A is the red boundary polygon and B is the boundary polygon. So when I call it as disjoint, when they don't meet, like in this figure, they don't meet, so we call it as disjoint. It is as simple as that. This is meet. They just touch the boundary, so the polygon A and polygon B meet each other. Equal to is just exactly equal to. In domain, they are exactly equal to. Their attributes may be different, but they are equal in space. That is, their area, perimeter, size, location, exactly is the same. So that is called as equal to. Here the red boundary polygon, black boundary polygon are overlapping but with 100% overlap. Then overlap is another relationship which is partial overlap, not 100%, not complete overlap. So we say A and B are overlapping. A is overlapping B or B is overlapping A. Now these are the relationships wherein we can exchange, like we can say A is disjoint from B and B is disjoint from A. But in this case we cannot say so. Here B is covered by A. We cannot say A is covered by B, but we can say A covers B. So covered by and covers are similar relationship. See, inside and contains. B is inside A, here B contains A. So again they cannot be exchanged. I cannot say A contains B and B contains A. Obviously only one of them is possible. But again these two relationships are the similar relationship. Other than these 8 relationships, there is a 9th relationship of distance. I would show you in an example how that works. It's basically like a virtual buffer. We say find out all the points that are within, let us say, 100 meters from a selected point. So that is using a distance relationship. So in total we have these 9 relationships. In ArcGIS you would find many more, but from these you can derive many more other spatial relationships. In fact, you can try to find out a linkage between these and the ones that are available in ArcGIS. Example of such a relationship is follows. Let us say we have these 3 features. Cities are displayed as points here. The blue points that you can see on the screen, dots are the black boundary polygons and highways are the red boundary, the red lines. Now you see that no element is selected here. Now my task is to select all the cities which are points in a selected world. This world is nothing but, it could be any world, but here in this case we are selecting a particular world whose number is available in the attribute list of this words as polygons. So this words as polygon layer would have a column called word number, which is 241 for this particular word. So how do I break up my task? I first launch an attribute query saying select the word ID equal to 241. That will give me this word. Now my task is to select the points inside this word. So I would use inside relationship on the selected feature in the word layer to get the desired result. I say select all the cities that are inside the selected feature, and the selected feature is ward number 241. So I get the cities as points inside this ward. Now this is an example of how we perform the queries, how we break up our task into smaller steps of spatial and attribute queries to find out a particular feature of interest. Other examples are as follows. Select all the features that are inside selected object. That was, I just showed you this example. Other than this, for example, if I wish to select highways that run partly through the state of Georgia, how do I do that? Because highways are not something that will be contained in a particular state. They are something that overlap, that cross over. So I cannot use the inside relationship. They are also not disjoint. The only relationship that would work here is the overlap relationship, because the highways always run partly through states. They are not contained in any state. Therefore, when I say first select the state of Georgia, now run an overlap relationship, that is find out all those linear features, the roads or the highways that are overlapping this state of Georgia. So that will give me all the highways that run partly from state of Georgia. So that is how we achieve this result. We select the desired polygons or the desired lines or features by using these spatial relationships. Another one is of distance relationship, as I told you. Suppose I have selected a point here. Okay, this point may be city of Atlanta or something, or it could be Dehradun or any place. Now I say find out all the cities that are within 100 miles of this particular selected point. So the system or the software on the background does not create a physical buffer, but on the background it will find out all the points that are within 100 miles by creating a virtual buffer of 100 miles, a fixed distance of 100 miles. So that is how it will, and then it will use the inside relationship and it will result in to all those points that are within 100 miles from the selected point. So this is how we use a spatial relationship for selecting the desired features. I have some assignment for you in this. So please note down the assignment. In fact, you already have these slides with you. So I would like to hear your answer after the break. Show steps to select all the states that are neighbors of the state of Georgia. What are the steps and what relationship will be used here? That is the question. Okay, so please try to answer this question. Then other question is, let us say I have two layers, a road layer and a building layer. So how will you select the major roads that are located within a distance of 200 meters from a hospital? Please notice here that hospital is a type of building and major roads are a type of road layer. So it is understood that this information is stored somewhere in the road layer and the building layer. Now these selected, just to give you an example so that you could imagine it nicely, these yellow points are the selected buildings, that is they are hospitals, and here the yellow roads are the selected, is the answer actually, is the all the roads that are within 200 meters from the hospitals. But how we do it in GIS is what is that you have to answer. Okay, so we move on to the next topic now. I would like to hear your answers after the break. The measurement operations are the second category of operations, wherein we produce some more information about the existing spatial features. Now we could have these raster and vector representations. The vector representation would have point, lines and polygons. So we can have measurement operations within each point, within each feature type, that is point or line or polygon, and right here on the screen two points, we can find out the distance. For each point, we can have the location, and also we can have point density. But between 2 points, we can have the distance. And the distance is calculated, you all know, by the Pythagoras theorem. The measurement between polygon features, if you want to find out the distance between two polygons, then it is not a straight line difference as it was in the 2 points. Then we talk about the minimal distance. That is, the distance from here to here could be larger, but the minimum distance is this. Right, so we can have actually various types of distances. The distance from the centroid of this to the centroid of this, like that. Then for the polygons, we can have area and perimeter, that you know already. Area and perimeter. Other than that, we can have centroid, and we can also have the bounding box computation. So what is that box, that rectangle, which completely fills this polygon? So the polygon is not extending beyond this box, and this is used in many things, including projections and so on. So in all calculations, even in subsetting and all, we do it using the bounding box calculation actually. So these are some of the operations on vector features. This is not all, but these are the most basic measurement operations. There are many more operations. Like I told, for points, you can have point density. Similarly, for the lines, you can have line density, and corresponding polygon density can also be there. Then you can have point and polygon. You can also have the distances between a point and a line. A distance, you can have all the densities, all the distances, minimal distance, maximal distance, distance from the midpoint of a line, distance from the farthest point on the polygon to a point. So all those are other possibilities. Then the distance of length in different directions is also possible, and this is something very useful for geologists. They use it for fault analysis, for all lineaments analysis, that how much length is distributed in each direction. And such a diagram, when plotted, is called as a Rose diagram. So you can have many more measurements, but these are the basic common measurement operations on vectors. Similarly, you can have measurement operations on rasters. Raster measurements include location, distance, and area. In fact, measurements are very easy and possible and simple, and we have the size of cell, which is constant. So for example, in this case, it is 30 by 30 meter pixel size. We can trace the location using an anchor point and the resolution of the grid. Area size, we can just calculate 30 by 30, so it becomes this much. Then distance again can be very easily traced out. Generally in rasters, until specified, the distances are calculated from center to center. For example, if I wish to calculate the distance between this cell and this cell, it will be from the center of this cell to the center of this cell. Okay. So the standard distance function applied to locations of their midpoints. And all the other things can be derived, whether it is pixel density or feature density or anything else, can be derived from just these simple measurements on location, distance, and area size. So that was about measurement. About classification, a lot has already been talked about. I'll just talk about what is left over, or what is more to talk. So M2N classification, you have already seen what is many to one, one to many, and one to one classification. I will just show you a few examples of these. And then user control versus automatic classification. Equal interval and equal frequency were also discussed, so I will not discuss upon that. But you all understand, I hope, the basics of classification, which means selection and presentation of selected layers of database based upon the classes or the values of a specific attribute. So we are basically reorganizing the information using selected specific attributes. The purpose of classification is to remove details from an input data set to reveal important spatial patterns, to reduce the number of classes, and to eliminate details. For example, I showed you classification of land use map into land and water. From 12 or 14 number of classes, we are reducing the information into only 2, land and water. So that is reducing the detail and highlighting only the important things that we want to see. Then we can also declassify in different systems for other purposes, for some specific kind of selection or so. We can also, erase out using the classification. We can also erase out certain information that we don't require. And we can also do it for recoding, reassignment of values in the cells. Classification types are when we do classification on something that is unclassified, the unclassified data, the original DEM values, for example, we call it as classification. But when we are classifying an already classified map, such as a land use map, we call it as reclassification. So that is the only little difference in the terminology. We also need to do some post-processing after classification is over. Sometimes it is required. I'll show you with an example in a minute. User control classification, when the user specifies the classification table. But when the algorithm decides how to break the classes, then it is called as automatic classification. There are two types of algorithms, equal interval and equal frequency classification. This is also known as quantile classification. In some software and some books it is termed as quantile classification. So what they mean is already explained. I'll just show you an example quickly of these. Here is a land use map which has got 6 categories. When I use an attribute called city blocks to reclassify it again using the city blocks, I get individual city block as one class. So there are so many classes now in the output map instead of the input map, as compared to the input map. So call it as one-to-many classification. Here we are specifying. In this case we are specifying more. We are basically disaggregating the information. Right? Many to one is just the reverse of previous one. Here we are aggregating information. From 7 number of classes here on the geological age, we are categorizing into the types of lithology, metamorphic, igneous and sedimentary rocks. So from 7 to 3. So that is many to one. 1 does not mean 1. 1 means less. M means more and 1 means less. So this is another example of many to one classification. Then we have one-to-one classification. Here we keep the number of classes same, but the classification scheme changes. You need to think and tell me, why would we require such type of reclassification of a scheme here? When the number of classes is same both in A and B, why do I need to change this? And what exactly this slide is doing for me? I wish to hear this from you. Maybe we can discuss after the break in the interactive session. So please keep your answer ready for this slide as well. Now, post-classification processing. This is an outcome after classification. You would notice here that these two polygons in the classified map, in the output map, belong to the same category. That is, suppose if this is, let us say, high income group, this is also high income group. But they are separated by this line here. Because they are joined, they are not disjoint, they should be merged as one polygon. And they should not remain independent, because now we are representing it as, let us say, based upon income group. And suppose they are falling in high income group, then they should all be merged together. So in such cases, we need to perform a dissolve or a merge operation to get the final neat map. Okay, so this is one example of post-processing. Similarly, you may need to do some more post-processing. Also, you may need to sometimes deal with other difficulties based upon classification scheme, etc. Now, user control classification, I would not discuss more on this because Raju sir has already discussed upon that. I would like to go a little further. Maybe this slide was not shown to you, so let me quickly show you this. Sorry for a lot of information on this slide, but I'll try to explain it to you. Here we have a continuous grid, let us say digital elevation model, which has got continuous values. The color does not mean specifically anything, because the black here is no data, and this means less elevation, and In this manner, we are going towards higher elevation. This is the classification table. From the continuous range of values, we are categorizing, we are making as ordinal data. That is, we are saying highest, then high, then medium, then moderate, and then low elevation. So we are trying to categorize into few classes from a continuous range of data. So this is again classification, but since the user is defining these class breaks and the definition of the output, therefore we call it as user controlled classification. Okay, so that was an example of user control classification where we also classify the no data. But here we are even trying to say some of the data which is not of interest to us, also we are categorizing as no data. And similarly, initial data. This simply means that we are interested only in the middle three categories. These ranges of values we are interested in. So we are putting everything else as no data. Now you can think of some examples of this. For example, if we are not interested in constructing our house at the hilltop or in the valley, we were interested in the in-between portions. So in such cases, we would like to mark some of the data with low DEM or high DEM values as no data. So this is based upon our requirement. We can orient it as we want and as we require. This was also talked about, so I'm skipping it. Now coming to the overlay operations, vector and raster based. The overlay operations, the concept was quickly explained to you that we require all the layers to be in the same spatial reference system and there has to be an overlap between them. Once we have this information fulfilled, then we can apply a lot of functions to produce a new map using existing maps. Right? So the principle of spatial overlay is to compare the characteristics of the same location in both data layers and to produce a new output value for each location. We can perform vector as well as raster based overlays, but if there is no overlap between the layers, then it does not make sense to perform an operation. Please always remember that. In the vector overlay, we have clip, erase, split, intersection, union, identity, and many more other operations. In raster, we have seen this arithmetic, relational, logical. Then I will talk about the local, focal, zonal, and global functions. So, just to explain you general principle of vector overlay operations, let us say I have map A and map B. The attributes are stored in the attribute table. Whenever an overlay operation is performed, new features are created. So now I have new is assigned to each of the new polygon. You can see that polygon number 1 in the second map is broken by, is cut into 2 by this line here in the A, and I am getting now 7 polygons instead of 2 and 4 in the input maps. The attributes from both A and B are copied to the output map. Whenever we perform overlay operations, if we are using the second layer only as a spatial coverage, we don't copy the attribute information from the second one, such operations are known as feature extraction operations. But whenever we merge not only the spatial information but also the attribute information, we call such operations as feature merging operations. I'll show you these operations. Now look at this slide. Here is the name of the operation. This is the primary layer, the input layer. This is the overlay layer. Okay, and this is the final result. So the first three ones, the clip, erase and split, are the feature extraction operations, while identity, union and intersection are the feature merging operations. What does that exactly mean? When we perform these operations, only the boundaries of these operation coverages or operation layers are used to work upon this primary layer. So in this case, for example, when I use this boundary as a clip layer, I cut the primary layer. All the information of primary layer only will be retained, but within the boundary of the clip layer. Similarly, in case of erase, the reverse is happening. That is, all the inside information is erased out, the outside information from the primary layer is retained. But no attributes from the erase or the clip layer are retained. Similarly in a split. But in case of identity, union and intersection, the attributes from both the layers will be copied to the output. The spatial features of primary layer and operation layer, how that is decided, that will depend upon the operation. For example, in case of union, all the features from both the layers will be copied to the output. In case of intersection, only the common information between the two will be copied to the output. So the corners from this rectangle are out. Similarly, these portions of the operation layer is also out. But in case of identity, all the features of the input layer, but only those features of the secondary layer which are inside the primary layer are copied. You can see here, these portions from the identity layer are removed because we are not interested in anything that is beyond our primary layer boundary. So these are the vector overlay operations. Then I would like to show you the raster functions also. Any function that is performed on a grid, whether in image processing or in GIS, can be categorized into one of these four categories: local, focal, zonal and global functions. Now what they are, to explain you quickly, local functions are those functions which work on cell by cell basis. Focal functions are the functions that work on foci of points. Zonal functions work on zone basis, while global functions consider the entire grid. That is why the name global. To show you a few examples of these examples are already covered, but what I wish to highlight to you is, when I perform such an operation, map C is map A plus 10, each cell is added with a value 10. So this is a local function. That is, each cell is being processed individually without being affected or without affecting other cells. So that is a local function. In case of focal function, the cell value of the central pixel is changed or is edited, is affected by not only the cell value but also its surroundings. And the surrounding is defined by foci of points called as kernel or moving window or focal. So that is why the name focal. So if I want to find focal maximum from this window, the maximum value here is 6.4, right? So the central value is replaced by the maximum value because we are performing focal maximum. Similarly, we can perform focal minimum, focal standard deviation, focal mean, or like that. So this is a function performed in foci of points, so we call it as focal function. All the image filtering operations are an example, or smoothing operations are examples of a focal function. Then a zonal function works on zone by zone basis. We have input raster as well as we require a zonal raster, that is a raster defining the zones. So in this case, for example, if I wish to perform a zonal mean or a zonal maximum, I have to consider what is the zone definition. So in this case, for example, if you look at this zone, the values here are 8, 4, 4, 2, 6 and 3. Now zonal mean of this will be calculated, and each value, each pixel in the zone will have the same value of this zonal mean that is calculated from this zone definition. So that is how we perform. Instead of foci of points, we are doing it on zone by zone basis. And finally, the last category of functions are global functions, which are performed on entire grid. An example is, suppose I have two hospitals. Suppose this is one hospital and this is a bigger hospital, number 1. Now, as a city administrator in an emergency situation, I wish to divide the whole area into these two, I want to allocate all these cells to one of these cells. To do that, I need to have some criteria. And since this is an emergency facility, I would like to have the criteria of distance. So let us say I wish to find out for each cell the nearest hospital. To do that, I need to find out the distance of each cell from both these source cells. So these are source cells. This 2 and this 1, 1, 1, these are source cells. So the distance from source to itself will be 0. That's why the value 0 here in this case and this case. But for this cell, for example, this is the nearest source, so the value 1 is placed. Please note here that there is uniform cost of travel from here to here, and the distances are calculated from center to center. If the cost of travel was different, then we generally do it from center to edge, edge to center. So for example, if the cost of travel to this cell was 2 and to this cell was 4, then this will become half of 2 as 1 plus half of 4 as 2. So the distance would become 3. But in this case, in this present example, there is no different cost of different distance travel. Therefore, the uniform values are placed here. So you can see which source is nearest to this source cell, and in this manner you can perform location allocation kind of problems. So that was about overlay operations, and now we talk about the neighborhood and connectivity operations. As I told you, lot of our decisions are based upon not only what is at a particular location, but also what is near us. So we are also concerned with the vicinity around us. For example, if we go to construct a house, we are selecting land. Now suppose these are 4 locations for land that I wish to consider for selection for buying a plot. So I would like to consider a lot of information such as how many people live there, what are their average household income, what is the income group of the people living there, are there any high risk industries located in the neighborhood. So basically what I wish to highlight here is that we are worried about our neighborhood. In such situations, we would like to find out what is our neighborhood. So we can have a straight line neighborhood, which is represented here as a buffer. We perform this in GIS using proximity analysis or buffer analysis. So this is a straight line distance of 2 km. Here, if the distance is not so straight line, for example, if you are walking on road, the road will not be straight line. It will be, non-linear. So in such cases, you can also find the non-linear kind of distances, and this is how you would get a result like this. You generally do it in network analysis tools in GIS. So you can consider your neighborhood and you can find out. Here is an example of how we can perform different, we call it as variable width buffer, the different distances basically. When we perform this buffer operation on only, using only one fixed distance, we call it as fixed width buffer. When we use different values of distance for different type of features, different category of features such as highways and roads, then we call it as a variable width buffer. This is basically an aerial expansion. Your input map could be, or input feature could be point, line or polygon, but your output will always be a aerial expansion, that is area or polygon feature. So we call it as aerial, so this is an aerial expansion of features. We can also have multiple ring buffer here. For example, let us say we want to calculate a buffer of 100 meters, but we don't want just one ring, we want several rings. So we can define how many rings we want and we can get this. This is all possible in any GIS software. The functionalities may be little different, some may be more flexible, some may not be, but these are very, very common functionalities which would be available in any GIS software. Then there was a question from the previous lecture about inverse distance weighting. What is inverse distance weighting? Somebody had asked. So I wanted to include this in my slides. To explain to you, this is basically a method of interpolation. This means that suppose we have collected some sample information for some points. Let us say here there are 4 points for which I have some data. It could be water quality data, it could be soil type, it could be anything, or air pollution or whatever. Now I have the data for these 4 points, but I want to get the data for the point for which I did not collect sample. That is, it is an unsampled location. So how do I find out value of, let us say, pH or any parameter of water quality or soil quality or whatever at this particular point. For performing this, first of all, you should know that it should be continuous data. It should not be classified or categorical data. It has to be a continuous grid, continuous data basically, range data also. So, how I calculate this? In case there are in fact lot of other interpolation methods, but what happens in inverse distance weighting, as the name itself suggests, we use the inverse of distance to weight the values here to find out the location here. The equation looks something like this. The value of the unknown sample z is equal to summation of 1 by d square, di square here, because d1, d2, d3, d4 are the distances for each of these points from this unsampled location, and zi's are the corresponding values here. So we weight the zi's here by their inverse square distances, and then we normalize it by this. This is just a normalization term, but this is a weighting term. We are dividing the values here by the square of the distances. What does this exactly mean? This is basically saying that give more weightage to the points that are nearer and give less weightage to the points that are farther. That is why the distance term is in the denominator and not in the numerator. So that is the method of inverse distance weighting. We could have simply 1 by d, we could have 1 by d square, 1 by d cube, or some other function. But all these methods are called as inverse distance weighting because we are using the inverse of distance to weight to find out the value of an unsampled location. We can also have other type of interpolation methods, but that is not part of this lecture, so I would not cover those. Maybe they are covered separately. Then network analysis, I would not discuss more on this because there is going to be a separate lecture. I would just try to tell you that since I discussed about neighborhood and connectivity operations, there is a lot of application of these operations in network analysis. In network analysis, we generally talk about linear features, and we try to represent and analyze all type of linear features such as rivers, roads, pipelines, etc. An example of network would be here. Planar and non-planar networks. We have planar network when we have simply one plane like this, like water, but here it could be like in case of roads, you could have overpasses and underpasses. Even in case of water, you could have nowadays, but whenever you have more than one planes, you call it as a non-planar network. You can have various kinds of analysis. For each type of analysis, you need to build a heavy network database which should follow certain rules. And impedance or cost factor is another important thing for the links as well as for the turns, for centers. So there are a lot of network features, 6 type of network features are there, for each of which you have to prepare a table. And once your network database is strong, then you can perform a lot of analysis such as ordered and unordered path finding. Here in case of ordered path finding, I wish to visit all the 4 points in a specific order. That is, I have to first go to 1, then 2, then 3, then 4. So, which is the optimal path? Similarly, in case of unordered path, I can say I have to visit these 4 points, but the order does not matter. For example, for a postman to deliver the letters, the order does not matter. He has to deliver in 1 day. So, he can choose so that he can optimize the distance. But in suppose in case of emergency, some accident has taken place, the order of the severity would matter. So in such cases, we would like to go for ordered path finding. We can also have network partitioning, as I told you, in case of some emergency facility or emergency situation, or even generally, like you want to divide the administrative area into, let us say, 5 physical health centers. So you would like to divide it based upon the distances, how fast they can reach if there is some emergency required. So we can have conditional, this is non-conditional case, and this is conditional allocation wherein you are putting some more restrictions. So that's why the polygon here has squeezed out, squeezed to a lesser Maybe we have applied some distance or some time criteria also, so that this polygon has reshaped now. So this would be discussed in detail in another class, but this is all you can achieve using the neighborhood and connectivity operations, which are again part of raster or vector GIS analysis. You can also do network tracing, like if there is a leakage, you can trace the conditionally connected or even without the conditional connection. For example, if suppose some leakage has taken place here, so you can check the uplink or the down networks, network links, so that you can find out which will be the areas which will be affected if a leakage takes place here. So which point is most important, which we should take care of first in such conditions. So that all can be analyzed with GIS using the network partitioning and the trace commands. There are many more other commands here. And finally, a list of all operations. Again, they have been shown, but I would just like to quickly add upon that. Single layer operations, when we perform them on one layer at a time, we call them as single layer operations. An example is buffer operation. Multi-layer operations, all topological overlays are an example of multi-layer operation. Geometric modeling, all the measurement functions are part of this. Point pattern analysis is basically finding out patterns of the point distribution. This would be specifically of interest to those who deal with the point features, such as distribution of some wildlife species, which is represented as a point. They could analyze the distribution pattern, whether it is clustered or it is random or it is regular pattern. So we can find out the nearest neighbor index, and there are many other indices which can be analyzed here. Network analysis I already discussed with you. It is about study of linear features. Then surface analysis, whenever we wish to study something on using the two-dimensional plane, we want to see a third parameter with respect to these two dimensions. So we can do all kinds of perspective analysis, like we can view the third variable as a perspective view, and can do all hill shading and view shed analysis, finding locations for watchtowers. Those are the applications of surface analysis. DEM is very much part of it. Then fuzzy spatial analysis. When we talk about zeros and ones, we are talking about the Boolean analysis. But when we move, we generalize this 0 and 1 into something in between. For example, the lights are on or off. But nowadays we also have dimmers. So whenever we say some value in between, we have to define the membership function of each cell. Let us say we are doing this analysis in raster, because that is more suitable for such type of analysis. We say that a cell is partly a member of 1 and partly a member of 0. For example, we say light is partly on and partly off. So in such kind of cases, we define membership functions, and we use fuzzy spatial analysis to represent the fuzziness of the nature itself. Because if you say where is the bank of a shallow river, there is no concrete crisp boundary. It is a continuous change. Similarly, the transition from one type of soil to another is also fuzzy. So to represent that fuzziness of nature against or in opposition to the crisp nature of the man-made features, we use the fuzzy spatial analysis. Geostatistical analysis is again statistics, classical statistics modified based upon the theory of regionalized variables. I'll not discuss much because the time is not there. Maybe we can have a separate session on that. And raster analysis, generally, I have discussed, these are basically, there are 4 operations: local, focal, zonal and global operations. All raster operations can be classified as one of these operations, and we can perform more or less everything that can be performed in vector can be done in raster, and vice versa. But there are certain things that are more suitable to be done in raster than in vector. I gave an example of fuzzy spatial analysis. And one live example is like fire progression. If we wish to study the spread of fire, so that will be more suitable to be studied with raster. But whenever we talk about something that is crisp in nature, we would like to go for vector based spatial analysis, because the boundaries are crisp and we can represent them in a better way using the vectors. So I think that is all I have. And finally, these are the steps. All of you have it. In fact, this is a simple thing that you can follow. Establishing the objective and criteria. Many people think that data collection is the first step, but it is not. First, we have to establish objectives, and criterias are to specify the objectives. Then we go for selection of right parameters. What exactly we require is what we define in step number 2. Then in third step, we go for data collection and we feed it into GIS system. In the fourth step, we prepare the data for analysis. In the fifth step, we also prepare the data for tabular and spatial operations. And finally, we integrate them all in step number 6. And then we evaluate and interpret the results. And finally, we refine the analysis if required. Otherwise, we go for production of the output results, and we generate the output and produce the report. So that was all from my side in spatial data analysis functionalities and tools. Thank you very much for your attention.